So let me tell you now how we split this problem in two. In the acoustic codes, basically we're going to compute explicitly all the acoustic waves, and we're going to model all the effects of convection and combustion in what we call the flame transfer function. So that means the acoustic world will basically be a code where we solve these equations. And the flame transfer function will be here. We'll start by saying if I have a given U prime at the inlet of the combustion chamber, I have a given Q prime at the outlet of the chamber. After a certain delay and with a certain amplification which is measured by N. Acoustic solvers will need a few things. They will need this flame transfer function, this element which is here. They will need to know also the sound speed field, of course, in the chamber. The sound speed field, you can obtain it by different ways. You can have a simulation, even a one simulation, where you know the temperature. So if you know the temperature, you know the sound speed field. You can have it from an LES, or you can even approximate it. It doesn't make a big difference. Usually you know what the temperature is. You know it's cold before the chamber, and in the chamber you know it's going to be close to the adiabatic flame temperature. So the sound speed field is not very difficult to use, and as I said, you need the impedances. That's also more difficult. So the two critical parts here are impedances, flame transfer function. This one is easy to get. How do you obtain the flame transfer function in practice? Okay, so that's an example here for a laminar flame stabilized here behind a wedge here. You have cold gases, hot gases. The principle is very simple. You send acoustic waves in this flame that will give you an oscillating velocity signal, and you measure the total heat release here versus time. So we did it here, for example, for a premix flame, laminar premix flame, and you can see here, after a few oscillations, we reach a harmonic regime where the speed at this point is displayed here, and the total heat release is displayed here. Those are two sine waves. You can measure the delay, and so you know what tau is. Okay, the question was asked, how do you get the delay? In that case, this is a good way to measure the delay in a simulation. You can do it in an experiment. In an experiment, you put a hot wire here, you put a photomultiplier here, which measures the whole flame. You plot the two curves, you look at the delay, and you have it. Okay? And to find the interaction index N, you normalize signals, and you can find it in the same way. So in principle, it's quite easy to do it. In practice, you're going to see, like always, it's not that simple. First, I've shown you this flame here. If I show you this flame here, which is a Siemens burner, by the way, there are more than one inlet here. So which one are you going to pulsate? And Q prime, just to do the simulation here, is going to be much more interesting. So FTFs today are obtained by different methods. They can be measured, and many labs do it because, as I said, it's enough to have a photomultiplier for the heat release. Well, some of you may be working on laser diagnostics or optical diagnostics. You know that the heat release is not that easy to measure if you have a diffusion flame. But if you have a premix flame and you measure, for example, OH, it's almost proportional to the heat release. So for FTFs, with a few assumptions, you can have a good idea of what the unsteady heat release is in the box. Or you can compute them if you have a good LES code, typically. Or if it's a small flame, you can even do it with a DNS code. There is a small problem here I didn't discuss yet, but you will see right away, is that to be able to do what I've shown you here, you have to have a stable flame in the first place. Because if this flame is already oscillating before you try to force it, you cannot do it. It's just impossible. So let me show you, for example, this flame here. It's already unstable. So I cannot force it, or I would have to force it very, very strongly because it's already unstable. So there is a small problem here, is that when the system is undergoing an unstable mode, you cannot force it. Just it's not compatible. Same thing for that flame, that experimental flame I've shown before. When this flame is oscillating like this, there's no way you can add here a loudspeaker. First, the loudspeaker will be burnt right away. That's a small detail. And also the strength that you would need for the loudspeaker would be too much. So there is a problem, is that when this system is undergoing an unstable mode, you cannot force it. You have to do something. What is this something? We have to make it stable before you excite it. And how do you make it stable? Well, you have to cut the loop here somehow. You have to separate the acoustics from this thing, okay? In other words, is to take the example of the Tacoma Bridge, for example. It means you cannot measure the response of the Tacoma Bridge when it's almost going to break. What you should do is come on a day where it's quiet and just hit it, you know, and measure its response in a stable case, not when it's fully unstable. It's too late there. So how do you do that? You need to separate you need to cut the feedback loop. You know that if you cut the feedback loop, then the system will be stable. You'll be able to measure the flame transfer function. How do you cut the loop? That's an interesting point. In a real flame, in a real combustor, what can you really do? Well, you cannot do that much, actually. You can change the acoustics. So typically, you can take the flame, take it out of the box. Okay, you have a combustion chamber. The chamber is like this. You take only this, and you go in the lab, and you create another system with only the flame. No acoustics here. That works, except, of course, that when you do that, you change the flame also, because now the flame being not confined, it will not have exactly the same response that you would have here. But it's not much of a choice here. The other solution is that usually, you know, these flames, you are equivalence ratio 0.75, it's unstable, but you go to 0.74, and it's changing. So you can go to a regime which is just near the unstable regime, and you measure the flame transfer function for this regime. In both cases, you're not exactly doing what you should do, but there's not much of a choice there. Of course, there is the ideal solution, which I've mentioned before, to use active control to make it stable, and then to add forcing on the actively controlled case. Something that no one has really done yet, but that'd be a good idea. Now, numerically, there is an additional problem which I need to discuss now. I haven't talked much about CFD here, but boundary conditions are a pain when you want to do this. Manipulating acoustic waves in a compressible code can lead to problems, and I want to give you an example. This is described in chapter 9 here with a method which we developed for compressible code, which is called NSCBC, and that's a big hit in the community. It's a classical tool to manipulate acoustic waves, and I want to show you what it gives on a simple problem. If you do a compressible simulation of a combustion chamber, you must specify the mean flow at the inlet and the outlet, mean flow at the inlet basically. You must be able to inject turbulence. I'm going to do a laminar case here so you can forget about turbulence. And you must manipulate the acoustic waves, everything together. And again, this is tough. So let me give you one example, which is again a small laminar flame on which we want to measure and compute the flame transfer function. This was done in this PhD here for the measurements. I'm going to talk about this paper published in Commercial Flame 10 years ago, and just show you that the intuitive way of doing pulsation is not that clear. You would say, if I have a combustor and I want to pulsate the inlet velocity, I have here, for example, the inlet of my domain. I'm going to impose here a velocity which is changing with time. Okay, like this. That doesn't work. You cannot do this. I'm going to show you why in a second. What you have to do if you want to pulsate a system is to send an acoustic wave there. Because when a loudspeaker is operating, it's not imposing a velocity, it's imposing a wave which is coming this way, because the point is that there will be a wave coming back. The velocity at this point is the superposition of these two waves. If you try to impose the velocity, you're actually imposing an impedance right away, and that's not going to work. Let me show you right away the illustration of that. So this is the setup. You have the loudspeaker here, the flame is here, everything blue is cold, everything red is hot. You measure with a photomultiplier, for example, the heat release here. So the first method is, let's impose here a fluctuating velocity. Remember, again, if you have done acoustics, if you impose a velocity, if you know about acoustics, that means that you impose something which is reflecting for waves. Imposing a velocity is like setting u prime to 0. U prime, of course, will oscillate here, but if there is a wave coming back, it will hit this zone exactly as if it was a wall. It won't be allowed to go through, so it will be reflecting. And that will mean trouble. So that means that here, the wave G here coming back from the flame to the inlet will hit the inlet and be reflected as another wave, and that can lead to self-excited mode. The right way to do that is to introduce only a wave here at the inlet. And there are methods to do that. This is the NSCBC technique here, which is mentioned here. And in that case here, we'll be able to control the system and avoid making it a resonator. So let me just give you the results. There are a few papers indicated in the notes here. The last version of the book contains actually most of the detail. Every year there are 2 or 3 new papers on these methods. And if you're developing a code for compressible flows, you'll have to go to that. You cannot escape that. So let me give you the first example where we actually impose here a velocity in a hard way, which is oscillating. We impose here the velocity to be sine omega t. And we plot here the velocity at that point and the pressure at that point versus time. So this is what's happening when you start oscillating the inlet here. The flame starts oscillating, but it sends waves back. These waves are reflected, come back, and they start playing their own game here, independently of what you do. So the flame starts oscillating more and more. Doesn't go to a harmonic regime, goes into trouble. Okay? And actually the code explodes a little bit later. So you see here that this thing is growing because in addition to pulsating this flow, you have allowed it to self-resonate, and that's bad. If you're using the other method where you use NSCBC at the inlet and you control only the wave amplitude, this is the movie I've shown before. In that case, when a wave is produced here, it comes through the inlet and it leaves. It's not reflected anymore. And here you get a nice harmonic regime in which you can measure the flame transfer function. So again, you shouldn't believe that measuring a flame transfer function in a code is just like that. You take the code and you force it. It's not going to work like this. You need to manipulate the acoustic waves, and that's not that easy. Okay, at that point, maybe I will jump to the examples and come back if I have time to the other things I wanted to describe here. But I think it's time to go to the case studies. The reason I wanted to present case studies for instabilities, I think it's because they are much more, I would say, closer to what you will live every day if you need to work in the field of thermoacoustics. So what is so I'm jumping a few pages, okay? I might come back to these pages talking about the Rayleigh criterion later, but this is probably too complicated for the moment. So let's talk about examples. Okay, so in the world of commercial instabilities, you see people coming to you and say statements like those which are listed here. My chamber makes noise when it's raining. I've gave you an example. My chamber melts, vibrates, quenches. And of course, what's interesting, especially in industry, but also in the lab, that no one knows what's going on, but everyone has an opinion. And of course, it has to be fixed yesterday. We had some examples in different companies in Europe recently where they had like 200 helicopters ready to be sold, but they were unstable. The engine was unstable. That means the lifetime of the engine was 12 hours. The customers were not happy about that. So basically, you didn't need much fuel for these things. After 12 hours, you had to change the engine. So you can imagine that in those situations, it's panic mode, which is the main goal. They create what they call a task force. Task force just is another word for we didn't do our job correctly. How do we fix the problem? Usually what you have to tell to these guys, it's too late, guys. You should have thought before and paid labs to help you instead of building things that don't work. But that's difficult to say at that point. Preliminary comments about things which vibrate. I mean, a frequency is just the ratio of a speed by a length. So anyone can take two things, make a ratio, and say, oh, it's 600 hertz, that's the cause of the problem. And we see that every day. So, for example, people take resonant mode of the structure, and if it matches 600 hertz, oh, this is the cause of the problem. So I just want to say that the fact that two things have approximately the same frequency does not prove at all that this is the same phenomenon. And the other thing which we see quite often is that things which vibrate for the cold flow, before you ignite the flame, are not necessarily the source of combustion instabilities. Unfortunately, because all these phenomena have similar ranges of frequencies, it's quite easy to be confused. And I will give you examples where really we are not helped there, because there are many cases where these frequencies actually match, but they are not the source of the problem. As I said before, what you see on the real engine and what you see on the laboratory bench will be the same only if you have the same impedances. If you don't have the same impedances, you cannot compare. So if you want to work on thermoacoustic, do not, write, frequencies equal that, so it's the cause of the problem. It's not true. You need basically to use these two tools I have presented: a large eddy simulation codes to do the full computation and to do the self-excited modes, also to do the FTF if needed, and acoustic codes to look really at all the modes in the system. So I want to illustrate that on a few examples, just to remind you that we're going to be using the LES code I've presented before, and we're going to be using a Helmholtz solver, an acoustic solver, which is following what I've said before. We freeze the flow, we solve the linearized Helmholtz equations. Just to show you the equation which is solved there, it's a wave equation in the acoustic code, where you need the sound speed, that's what I said before. You need the flame transfer function. So the sound speed comes from LES or from once. The flame response, that's the flame transfer function, comes here. And you need the impedances. Once you have all these ingredients, you can run your acoustic code. And you have to remember, typically, acoustic codes, 100 hours, LES code, 1,000 times more. So it's really worth working with the acoustic code as much as you can. So I want to start with a classic configuration, which is the DLR swirled engine. It's one example of what we do in Europe. It's an engine. This part here comes from Turbulent in France, and it was plugged on the chamber which is installed at DLR. Europe is really giving money to people who work together. So in a system like this, you had also Siemens as a partner. We basically mix elements coming from all over Europe. We install that somewhere in Europe, in that case at DLR, and then we try to compute it. And this paper, 2005, here is one of the reference papers for LES. If you want to compute it, it's really one example. We have a lot of data. These guys at DLR provided almost everything, including the species. Of course, it's different from the real engine, because in the real engine, you don't have a square chamber here. Okay? You put a square chamber here to be able to do laser diagnostics, to have windows everywhere. In the real engine, you would have 16 of these burners in the system like this. So here, that's what you do in the lab. This is the typical combustion, the computational domain we're going to use. So you have here the plenum, where you mix the gases entering here. Here you have the swirler. Here you have the chamber. And here you have the atmosphere, and you mesh the atmosphere too. Again, it's a problem of boundary conditions. We don't want to stop the computation here. We think it's more precise to mesh also the atmosphere, make sure that we get all the reflection coefficients right here. The mesh looks like this. This is the geometry, it cuts through the geometry. It's an unstructured mesh. To give you an idea of the evolution of codes there, this mesh here has about 1 million cells. It was in 2004. Now we do the same computation with 2.8 billions. Okay? Fortunately, when you go from 1 million to 10 million to 2.8 billions, the results don't change that much in the field of thermoacoustics. You just wait longer. Well, not really, because the computers have improved too. The nice thing about this computation setup is that there is no boundary condition to set up except to say that the pressure here is 1 bar and the flow rate here is imposed. Apart from that, you don't have to do anything because you solve the flow in the swirler here. I want to mention that too, because I know quite a few groups which begin the simulation here. So they drop completely that. They start the computation here where they impose the velocity field. They impose the rotation, they impose the actual velocity field. It's much easier, of course. But you lose a lot of things because a lot of things are actually happening here. And if there is a combustion instability, it will actually propagate everywhere. So it's much better to compute the whole flow. Of course, it's much more difficult. Okay, as I said, we won't have a boundary condition here because we compute the whole thing. Here there's a small detail. Of course, this is an inlet, and we don't know the inlet impedance here. And so we decided to impose the velocity, to check it as a velocity node, and we checked later that it did not play a big role on the results because the section here is small compared to the overall section. So actually, there's a velocity node almost here. But it's one of the limitations here in terms of thermoacoustics. So this is a cut here of the pressure. This is wet, this is high pressure, this is low pressure. And you can see also the velocity field. This is obtained by LES. And right away, you recognize it's LES because you have vortices. It's unsteady. And The instantaneous velocity field shows right away here that there is a big recirculation, and this complicated pattern that you will find in most swirl burners when you do that. Of course, if you average the LES, you find something which will look like once. Okay, this is the average velocity field, and if you would run once, I will show you once result in a few minutes. This is what you would find with Reynolds average methods. But here, Reynolds average results can be obtained from LES, but of course we don't use them for acoustics. So just to make sure that we get the results right, and I'm coming back basically to turbulent combustion issues, I want to show you a few results here and compare them with ones actually. These guys in Germany did a good job of measuring velocity profiles everywhere. So I'm going to show you velocity profiles in this system and compare them to different codes that were used for this guy. I think this is non-reacting for the moment. So those are the different cuts in the burner, and you have 3 codes here. The red code is the code from Stanford, CDP. The black one is our code, AVBP, with a high order scheme. And the dots here are the measurements. And you recognize it's a swirl burner because this is the actual velocity. You see on the axis the velocity is negative. So the flow is going from the outlet to the inlet there. And this zone is pretty strong. You can still have recirculation zone here and there. And even at this location here, if I come back to this one, even at this location here, you are very far from the end of the recirculation zone. So you see the recirculation zone is huge in a burner like this. And this is a burner, the injection is really the one you have in an engine. So this is really very close to engine conditions. Apart from that, you see that LES is doing rather well everywhere, capturing the mean velocity profiles with precision. Of course, the French code is doing better than the American one. So this is when things get more interesting. This is not the velocity, actual velocity, it's the RMS of the actual velocity. So it's U prime as a function of space. The first thing you see on these burners is that the U prime here is huge. It's 15 meters per second. You compare it to the mean velocity, which is 20. Well, it's 20 here, but here it's almost 0. That means the U prime is much larger than U bar. So that's a typical feature of swirl flames, that they have very large levels of unsteadiness in the burner. The second thing you see is that LES is doing amazingly well in predicting the level of U prime. Remember, U prime cannot even be obtained with ones because you don't have a U prime. You have K, the total kinetic energy, U prime square plus V prime square plus W prime square. You don't have the individual components. So LES here is really doing very well. This is the azimuthal velocity. So this is the rotation of the flow like this, you know. And again, you can see it's large, 15 meters per second. This is just in front of the swirler. So this is where the swirler is making the flow turn. And you can see that the comparison with the experiment is quite good, except here, where certainly the experiment is wrong. We don't know. Same thing for the RMS azimuthal velocities. You can see also the very large values on the axis, and the comparison with the experiment, which is quite good. Now, if you start looking at this thing, you see here, you might wonder, why do we have such high level of turbulence on the axis of a swirl burner? And here, it comes back to what I've told you. It's really the trace of this PVC I was discussing yesterday, the precessing vortex core here. You can even see it in the simulation. Even in 2004, we were able to visualize this thing easily. This is an ISO surface of pressure, which basically tracks the place where the vortex axis is located. And when you animate this thing, you see it has this usual shape here. The very interesting point about PVCs in real swirlers is that you have only one finger here of low pressure, but you can have more than one. You can have 2, 3, 4, depending on the swirler geometry. And that makes things more interesting. This is the same visualization on the side. You can see this finger is turning around the hub here. You can see it turning around. So it's the hub is here, and the axis of the vortex is actually doing that around the hub. Okay. Now, interesting question is, of course, what will this thing do to combustion? And I'll come to this in a second. Before that, I want to compare once to LES for this flow. We went here, I guess it was CFX, because Fluent couldn't do it at that time. So I'm going to show you once with CFX and LES with AVBP. So here, the red curves are the ones, and the black curves are the LES again that you've seen before. And you can see that already for the actual velocity, the once has problems, and it's far from what it should be. It's far from the LES and far from the experiment. For those of you who are, well, maybe not, you are too young for that, but for once codes, people know that in once codes where you look at swirling flows, you have to modify the Computational model. They know that's the usual problem with once. You need another model for each flow, basically. But when you have a strong swirl, we know that the Computational model is not good. You need to do corrections on it. They were not done for that case. And you look here at the azimuthal velocity, it's the same. The once formulation just misses, the swirl, basically. And the other problem, which is classical with once, is that since it's too dissipative, it kills the vorticity, it kills the mean velocity. You see here, it's not swirling anymore. This result is very close to what I've shown you yesterday. If you lower the code, it kills eddies. And the swirl is just another eddy. Okay? The swirling flow is just another vortical structure. So it's dissipated, again, by turbulent dissipation, turbulent viscosity. Now, the most interesting thing here is the turbulent kinetic energy. The once code cannot give you U prime square, but it can give you K, the turbulent kinetic energy. And those are plots of the turbulent kinetic energy. This is the experiment. This is the LES, and this is once. Okay? So here, the error on K is huge. I mean, it's a factor of 20. And you could say, well, we don't care, except that K is the input that will be used to build the time to compute combustion there. Remember when we wrote the eddy breakup model yesterday, we wrote temperature multiplied by 1 minus temperature divided by epsilon over K. So the K here, which will be used in the once code, is just wrong by a factor of 20. So then it means when you go to combustion, you're going to have big problems. Okay, I want to go back now to LES. At that time, we had a student in Toulouse. We sent him to DLR. And the first thing the guys told us when he was at DLR, he told us, we are in trouble because at DLR, they see a PVC, like I've shown you, but not at the same frequency we see in the LES. Okay, when people tell you that, say, okay, where did they measure that? Well, they measured pressure in the plenum, not in the chamber. And they said in the plenum you have a 300 Hertz mode. So that was the signal they had for pressure in the plenum with a peak here at 300 Hertz. So we went back to the LES, and we looked also at the plenum because we didn't do it before. And in the plenum, indeed, we found also a 300 Hertz mode. But we told them, well, stop looking at the plenum. Look at the chamber, because in the chamber, you should have a 500 Hertz mode. And by the way, it shows how complicated these things are. You can have a system where you have frequencies, but not the same everywhere, depending where you are. And one of the reasons for that is that the PVC is not something which makes a lot of noise. So the noise of the PVC does not propagate in the plenum. In the plenum, you have another mode. But when you go to the chamber, what you see is really the signal of the PVC. So we told them, put a sensor very close here to this zone. That's what they did in the experimental data, and showed that they captured the 500 Hertz mode. So by the way, you see it's very important if you're comparing with someone doing an experiment, not to wait until they finish, but you have to work with them right away to ask them to redo measurements if you don't find the same thing as they do. So it really proves that in the chamber, the 520 Hertz is due to the PVC, and it's there both in the LES and in the experiment. Now you ignite this thing. Okay, you have to get your 3D goggles to understand there. The shape of these flames in swirl flows is very specific. Okay, the flames almost always look the same. If you have a swirler like this with a wall here, a hub, here there is a recirculation zone, so the flame will be stabilized here and here. And in addition to that, there is a recirculation zone here also. So what you see as a shape is something like this. Okay, that will be the typical shape in most swirl combustors. And it's due to the fact that you are recirculating here and recirculating there. Depending on the case, you will see flames stabilized here and here or not, but you will always have this zone here. Actually, the flame has to stay there. Remember, we use recirculation to keep the flame anchored here. So now you look at that with an iso surface of temperature, you're looking at an animal which has this shape in 3D. It's like a donut without a hole in the middle. I don't know. It's this guy, okay? you see there's a hole in the middle, and that's a flame surface colored by the velocity. So after a few years of doing that, you get used to it. Or you can also use 3D systems to take a look at it. So same thing here for combustion. You can compare the measurements and the LES, and you see it's very good. You see that the profiles are much flatter here, and the recirculation zone is even larger. Look at this recirculation zone here. With a constant velocity, it's taking a big portion of the engine, and this is really the place, all these points here recirculating are really stabilizing the flame. They are there to do that. So the actual velocity, the IMS actual velocity, and here I'd like to come back to something I said also 2 days ago. You want to compare LES and experiments in a case where density is changing. You have to be extremely careful when it comes to IMS values. This is the experimental data. This is the LES average data. Between the two, this guy has to be always smaller than that one, because from here to there is the unresolved subgrid scale variance that has to be added. So you can say also something is that in places like, there are very few here. No. Normally, this curve of LES should always be less than that one, okay? Otherwise, there is a problem. In most cases, it is, okay? You see it's below, except a few points here. But otherwise, the agreement between the two is still very good. This is the azimuthal velocity, and you see that the swirl has changed here. There's a zone in the middle which is not even swirled, because the recirculation zone is so big now that in the center, it's almost not swirling. But you see, again, the agreement is pretty good. Same thing for the IMS azimuthal velocity. So now we moved from, yeah.
The agreement are pretty good, but I just want to know, like, what are the chemistry model that you talked about yesterday?
Yeah, I mentioned that at the end of the turbulent combustion course. I will use the second flame model everywhere. Everything you're going to see here is with the second flame model and with a one-step or two-step chemistry.
So this is the third method, reduced scheme.
It's a reduced scheme, two-step. But again, when you go to thermoacoustics, the details of chemistry are not so important. You just need the right flame speed, the right flame temperature. The rest, I believe, is not that significant. Okay, so for this reacting case, what we saw in the LES is that we had an unstable mode at 500 Hertz. And people said, 500 Hertz. We saw that in the non-reacting case, we had the PVC at 500 Hertz. And it's also something you see quite often in industry. People say, I have this mode at 500 Hertz without combustion. I ignite the flame. I see 500, so it's the same. So the instability would be due with combustion to something which was there without combustion. But in practice, we proved that it's not the case. And again, if you want to prove that, you need more than intuition. You need, to go to the simulation. So what we did here, we're going to apply the acoustic analysis to this system and plot, for example, the pressure signal. You can use an acoustic solver for that and plot the P prime signal here on this line, and then you can measure the P prime in the LES too. And this is what you obtain. So this is the axis of the burner. This is the outlet where P prime goes to 0 almost. And here you have the signal obtained by the LES. And here you have the signal given by the acoustic solver. And you see that the agreement is extremely good, suggesting that this 500 Hertz stuff which is there is really acoustic. It has nothing to do with the PVC. And it's really due to an acoustic mode of the system. By the way, just a small comment here. This zone here is the throat of the burner. It's this zone here. And it makes sense at this location that you have more P prime in the LES than in the acoustic solver. Because in the LES, you capture P prime due to everything. That means vortices and acoustic modes, while in the acoustic solver, you capture only the acoustic part. Remember that in the real world, a pressure fluctuation can be due to an acoustic wave or to the center of a vortex, for example. So LES captures both. This is why normally you should always have larger P primes, especially in the zones where you have a lot of vorticity, larger P prime in the LES than in the experiment. Okay, now let's increase the size a little bit. That was a small burner. Now in Germany, they're not afraid of big burners. So we're going to talk now about this guy. This guy is one injection system in a gas turbine, which was called the VR84 at Siemens. This is a 300 megawatt system, where they use 24 of these injection systems. This is very big experiment. So what they did, they took only one sector and they installed it at ITS, which is an institute in Karlsruhe, and they did a lot of measurements on that. So this system is much more complicated. I've shown it before. You have a diagonal passage here with veins. This is where they inject the methane. And in the center, you have an actual swirler with additional veins. And you have to measure and compute all these things. Typically here, it's what we call today a small simulation. Okay, it's only 2.6 million tetrahedra. That's an old computation. I think I have a movie here showing the geometry of this thing. Would that work? Yeah. So again, same idea. You take the burner coming from a real engine, but you plug it onto a cubic combustion chamber so that you can do optical measurements. The chamber is terminated by a nozzle, which is square too. You need to add a nozzle to close the recirculation zone in these systems. Otherwise, the recirculation zone could be big and even get out of the combustion chamber. So you inject air through the wet zone and through the other one here. So air coming in here and coming in here. All this zone is recirculating here, and the flow actually enters here and just goes both ways because of the very strong swirling motion. A flame in a system like this is very strange behavior. You recognize the shape I have drawn on the board here with a center recirculation zone. Except here, as you will see in a second, this flame is very influenced by acoustics, and I will come to that in a second. This is a cut here through the chamber without combustion. This cut here is in this zone here. You can recognize all the points which are within the black line are recirculating. And you can also recognize here the PVC. You can see it's turning here. This is a trace of the precessing vortex core that is found here without combustion. You have one exactly like we had before in the other system. And exactly like we had for the previous system, we are able to measure, well, not we, the Germans measured the velocity profiles here, which is quite difficult in those very high power systems. And you can compare them to our LES. So this is the comparison of the measurements and the LES. You see that the agreement is still pretty good. You still have this very big zone of recirculation, but of course, it ends up closing here. And how to say that? This doesn't look like the flow I've shown in the first combustor. Each swirl combustor has its very specific shapes, you know, and there is no general rule here when you look at a system like this. This is the RMS actual velocity. Same thing, the agreement is quite good. You still have problems at different points, but considering the size of this engine and the power and the difficulty of performing measurements, it's quite a reasonable agreement. Now, as I said before, you want to be careful when you compare things because you are comparing Favre averages with Reynolds averages, and you get all these problems I discussed yesterday. I don't want to go back to that. Even when you talk to them, knowing if they measure Favre or Reynolds average is quite difficult. This is the swirling flow. So this is the swirling component, the azimuthal velocity. And again, you see you capture the experimental data really well. And this is the RMS swirling velocity. Always the same thing, as expected. Normally, the LES should be below the experiment because we should add the subgrid scale component if we want to be on the curves here. So this is a visualization of the PVC there. You see this thing is turning, usual shape. There's only one finger, and it's rotating along the axis of the burner. Now, this was for non-reacting cases. Now, you ignite this thing. The first thing which happens when you ignite is that people go away because it's making a lot of noise. The noise that is observed when this thing is operating is of the order of 250 hertz. And you have here a stability map, which is typical. For an occurrence ratio of 0.5, you have almost no noise. A P prime, you see, is almost equal to 0. And when you get to higher power, occurrence ratio of 0.8, you go to a P prime of the order of 6 to 7%. And 6 to 7% is a lot of noise, okay? It's 6,000 Pascal. Again, your ears would be dead. So the funny thing, again, is that this frequency here matches almost the frequency of the PVC that we saw without combustion. And so people at Siemens were saying, hey, it's the same. So this instability is due, again, to the PVC. And we investigated this question, and again, we showed that it was not the same source. How do we know? Well, again, you run the LES of this system with combustion this time, and you look at what's happening. The first thing that you see, this is now the shape of the flame when you go to reacting cases. And when you look at the cut now with combustion, you see, of course, the flow is quite different. You have everything here is hot, and you see that the PVC is going away. Actually, I have a picture, I think, here. Does that work? Yeah, you see the PVC at the beginning of the simulation, and you see it's going away. You make it longer, there's no PVC left. So with combustion, there is no PVC in this system. So the PVC that you saw for the cold flow is not the source of the problem that you have when you ignite a burner. The second thing we did is to compute this system with the Helmholtz solver. So we did a computation with the Helmholtz solver, and the Helmholtz solver gave us all these frequencies here. That's the very funny, interesting thing in the real burner is that there are lots of frequencies. A complex shaped burner can have a lot of acoustic modes. It's actually up to the combustion now to pick up the modes they like. So in this system, you have a frequency here. This is what we give them number, and this is what the LES was seeing. And the LES was seeing a mode with combustion at 159 and 750. But the LES did not see the 250. The experiment was seeing the 250, AVSP was also seeing the 250. So we said there is a problem here. Why do we capture this mode with the acoustic code and not with LES? So again, there were big meetings, people fighting all over the place. And we said, okay, the acoustic code gives 250, the experiments gives 250, why don't we see it in the LES? So you come back, ask the PhD student, what did you do exactly? And the guy said, well, it's always his fault, okay? And the guy said, well, I don't know, let's go back, take a look at the results. This is the result of AVSP, of the acoustic code. Look at that, of course, when you look at the unsteady velocity, you see it's very large here. That makes a lot of sense that it's large here. It's the sensitive place for combustion. You'll have large velocity fluctuations. So this is consistent with what we see in the experiment. So why is it not working? Well, it's working certainly with the acoustic code. We can predict the frequency of the acoustic mode with the acoustic solver, and it's increasing exactly like it does in the experiment. So again, back to the PhD student, what's going on? This is the mesh of the computation with the acoustic solver, and this is the mesh with the LES. And the day we got this picture, we said, there's a difference between the two. Look at this one. This one has the plenum included. This one does not have the plenum. The computation in the LES starts here, where we impose the velocity. So we are back to this question I discussed before. We made the classical mistake of assuming that impedances were simple. But actually, impedances here, the impedance is not infinite here. The impedance depends on the plenum. And the acoustic code sees that because we have included the plenum, and the LES, because we wanted to save mesh, doesn't see it. And so when you look at the mode, like the 250 Hertz mode, it's a mode actually which is controlled by the plenum. If you remove the plenum, it's gone, and the LES cannot see it. So you have a very nice, very expensive LES, but you have just thrown away the most important part, that you didn't have the plenum in the system. So the conclusion for the Karlsruhe data was that when you ignite combustion in this burner, you have a mode which is due to the second acoustic mode of the whole setup, and it's not due at all to the PVC, and you won't see it in the LES if you don't include the plenum. Now, does that mean that there is no mode at all in the LES? Well, not really. When we looked at the LES, we saw other modes, higher frequency. I want to show you the pictures because they're cute here, and they show also that you can capture other things here. This is a result of the LES showing the P prime square field on the walls. And when we look at that, you see right away that there must be something going on here in this system. P prime tells you that there are very large fluctuations of pressure at these points. And so you can visualize them looking at instantaneous field like we did here. This is the instantaneous pressure on the wall, and here you have the flame movement. Now, this is where things get really complicated. This thing is turning, remember? It's swirling. It's swirling in this direction. Huh? But the mode here is turning in the other direction. And of course, the mode is acoustic. So it's turning at the sound speed, while this thing is turning at a much lower speed. There is an interaction between the two. Huh? You can visualize this mode here by putting sensors at the wall here and on the wall going downstream, and you will see that all these sensors are in phase, showing that the mode has the same phase from here to there. So it's there's no activity, well, limited activity in longitudinal direction. Can you move or not? Yeah. So you see all these pressure signals are in phase from here to there. So it really says that there is no activity in this direction, or at least it's coherent. It's what we call a half-wave mode or a quarter-wave mode. When you go in the other direction, now you put sensors in the corners. In the LES, you see that. And you see here that these things are shifted by 90 degrees. So it's really the picture you see here, that this mode is turning in the LES. So now you say, OK, can we explain that? Well, actually, you can now, because this thing takes place only in the chamber, not in the plenum. So if you go back to the acoustic solver, you find indeed that there are two modes, acoustic modes, at about 1200 Hertz, which is exactly the frequency we saw in the LES. And these two modes are degenerate. OK, I'm not sure I want to go too far there. What you mean by degenerate, that means they have the same frequency, but they are turned by 90 degrees. This one actually is exactly like that one, but turned by 90 degrees. And they constitute the basis for all the modes that you can create there. These modes, I will come back to that for the azimuthal burners, can be either standing or turning. In that case, they are turning. You can take these two modes, the mode which is like this, the mode which is like that, and combine them. This is what I did here. So this comes from the acoustic solver. There's no LES at all here. And when you combine these two modes, this is what you find. Maybe. Doesn't want to. Do I have a problem here? I haven't had any problem up to now. Huh? Looks like this guy is gone. OK, so maybe we'll have a break now until I fix this thing. Huh? We're a little bit early, but that's OK. Ah, no, it's coming back. Is it? It's thinking about something. Yeah, store. Yeah, it's back. So you can see here that just by combining these two acoustic modes, we have exactly the same features that we saw here, okay? This turning mode here. So it really means that the LES is capturing another of these acoustic modes which are here. And this is a mode which is turning in the burner. So to conclude for this case, the cold flow was dominated by this PVC, but the PVC goes away with combustion. So if you see something with combustion, it's not due to the PVC, even so it's the same frequency. Don't worry about frequencies, it's not sufficient. And in addition to that, we can say that it's controlled by the plenum, which is also interesting because in Karlsruhe, when they designed the plenum, they used any plenum. You know, they just put a plenum. But in the end, everything was controlled by the plenum. So it's again the same problem. They thought that the chamber was the problem, but if you fit it to another plenum, what you really get in that case is something which is controlled by the plenum. And it really, again, says that if you're looking at thermoacoustics, you have to worry about what you put at the inlet and the outlet of the chamber. OK, we still have 15 minutes, is that right? I'm always lost here. We have to finish at 12, 5 minutes. OK, 5. Not the same. I want to talk about another burner here, which was also a European project. And this one was installed in École Centrale in Paris. It's a more complicated burner in some sense because there are lots of injection devices here. So basically, this is a wall. You inject through this chamber by these devices here. And here you have a backward-facing step, and the flow is going that way. So this is the shape of the description of the burner. You inject premise gases here to make it swirl again. And when it reaches the chamber, then it flows down and gets out through the outlet on the right side. So this is the burner injection here. This is the commercial chamber. The reason I want to show you that is, again, to discuss the influence of commercial instabilities on the system, and also to illustrate the effect of acoustic impedances on this problem. So what I will do is I will compare that also to experimental data, but I want also to show you that I'm going to do a simulation, and the only thing I'm going to change is the acoustic boundary condition on the outlet. Again, with an SCBC, you're able to decide that this outlet is non-reflecting, or you can make it reflecting. And just by changing that, I want to show you that I will change the level of some acoustics in the problem. So I have a scenario that we built versus time. We will start by having a non-reflecting outlet, then we'll make it reflecting for a certain amount of time, and then we'll make it non-reflecting again. Okay? And it's the only thing we change in the simulation. All the rest, chemical scheme, chemistry, whatever, mesh, everything is the same. We'll try to do something also which was very difficult actually to do at that time. Even today we have problems to do that. We'll try to check all the terms in this equation. You see, this is the balance equation for the acoustic energy, the variation of the acoustic energy in the box, the fluxes on the boundaries equal to the Rayleigh criterion. Quite often, when people do things like this, they plot for you one of these terms alone. And we decided that this was not sufficient. If you want to believe one of these terms, what you have to do first is to compute all of them and prove that the sum is equal to 0. That's much more difficult. It took us a long time. Again, the PhD student was exhausted at the end. It didn't work for a long time. So let me show you how the simulation works, and then we'll just take a break. So this is the setup again. You're going to see many things at the same time. So I'll stop the movie for the moment. So this is first non-reflecting outlet. Then we'll go to reflecting outlet, and then we'll open the outlet again acoustically. Here you will see the acoustic activity in the burner, and here you will see the total acoustic energy. So this is the acoustic flux at the outlet. This is the total acoustic energy. Here you have the velocity, and here you have a flame surface colored by the velocity. So when the outlet is acoustically open, there's not much activity. You see the fluxes are small and the acoustic energy is small. As soon as I will close down the acoustic condition, which is somewhere here, you will see that the flame will start shaking more. Then it goes to limit cycle, and then when I will open the outlet, it will stabilize again. So you see now we are closing the outlet. So the flame starts shaking. You see the pressure increasing. You see how this thing, starts moving. You even see flashback in the system now. And now we're reaching the limit cycle. You see this flame oscillating very strongly, so strongly that it actually even flashes back in the system, comes back. And then we open it again. Not now. The limit cycle is here. We're going to open it. Up. And then the flame dies again. Well, the flame oscillations die again. Okay. And then at the end here, we are back to a very quiet flame, exactly like we had at the beginning. Okay. And you see, again, that when you talk about combustion, I understand it's quite logical that people come to you and tell you, well, do you have reaction 224 about the oxidation of HCOO+? I keep telling them, well, what's the boundary condition at the outlet? Because in most flames like this one, when they are confined, the boundary conditions are more important than all the rest because they change the flame in such a way that you cannot ignore that. So you see here, the only thing we change, boundary conditions, we can do what we want, and we're going to use this set of data to analyze who is responsible for the instability there. I will do that after the break. It's time for the break now. Thank you. If you have questions, or maybe during coffee if you want.